Welcome to Lesson 2, Energy Changes in Chemical Reactions. Our lesson objectives: determine if a reaction is endothermic or exothermic, use table I to identify the type of reaction, and determine if a reaction is spontaneous. Recall that delta H on table I is called the heat of the reaction. That means it's the net or total amount of heat energy that's either lost or gained throughout a chemical reaction. And the delta H can be calculated out by looking at the energy of the products minus the energy of the reactants. And that change, that delta H, is called enthalpy. Also recall that we have conservation of energy in a chemical reaction. That means the total energy on the reactant side equals the total energy on the product side. What you put in is what you get out. So if the energy of A is 40 kilojoules and B is 20 kilojoules, and we're adding 50 kilojoules of heat, this is an endothermic reaction, 50 plus 20 plus 40 gives me 110 kilojoules, and that means the product is also going to be 110 kilojoules. Now let's look at the types of chemical reactions, endo versus exothermic reactions. In an endothermic reaction, we are adding heat to get the reaction going. Heat is being absorbed by the reactants, and that energy then is stored in the chemical bonds of our products. And so the delta H, the change in heat overall, we're putting more energy in than we're actually getting out. And so we have a positive delta H. And you can see that energy is listed as a reactant. On table I, here's an example of an endothermic reaction. Here, you'll see that the delta H is listed as a positive. So it's a positive 182.6 kilojoules, meaning it needs that much energy as a reactant to get this reaction to take place. If you forget this, on the bottom it tells you that a minus sign is exothermic, so therefore a plus sign is going to be endothermic. And so where would that energy go? Again, at a reactant side, so I'll be adding it to the left side of my reaction. Exothermic reactions, exo meaning exit, therm meaning heat. Heat is being released or exiting. It's being released as a product. So overall, it's giving off more heat than it needs to take in. And so the delta H is a minus sign. And exothermic reactions, because we're giving off energy, it's a more stable reaction. It's also spontaneous, which means these reactions happen essentially on their own and happen more often in nature. And so we'll look on a reaction, we see that energy is now on the product side. It's being released as a product. And this would actually feel hot if you felt this reaction. So looking at table I, you can see that the delta H is negative, indicating a loss of heat, or it's giving off heat energy. And in terms of placing it in the reaction, we would put it on the product side. So it's CO2 as a product plus 393.5 kilojoules. Notice I put a plus here and not a minus sign. The minus is telling us that it's exothermic, but we're putting in as a plus in our reaction. What happens if the reaction that you have is reverse of what's on table I? So for example, if you had a question, what is the delta H in the following reaction, and is it endo or exothermic? So here we have the decomposition of water into hydrogen and oxygen gas. But on table I, it's the opposite. It's the synthesis of water. And so if the synthesis of water is negative 571.6, so it's an exothermic reaction, meaning energy is on the product side. If I go in the opposite direction now, that means the sign is going to switch. The magnitude, the number doesn't change, just the sign. So if looking at this reaction, since it's reverse, it's going to be a positive 571.6 kilojoules. So it's endothermic for the decomposition, and then on table I, for the synthesis, it's exothermic. Let's check your understanding. Can you determine if a reaction is endo or exothermic, and can you use table I to identify the type of reaction? Lastly, let's look at spontaneous reactions. A reaction is spontaneous if it occurs on its own once we get it going. And so exothermic reactions are spontaneous because they have a lower activation energy, meaning they take less energy to get the reaction going because we don't have to add additional energy to get this thing to take place. Spontaneous reactions are also when we have an increase in entropy. Recall that entropy is essentially the disorder of the system. So if a reaction is getting more disordered, higher entropy, it is going to be spontaneous. And recall that entropy is really the number of possible arrangement of particles that we could have. So if we look, for example, at a solid is very ordered, and there's not many ways we could arrange these particles in a different arrangement. Whereas we get to gas, since the particles are very spread out, very disordered, there are many different possible combinations of these particles in terms of their arrangement. And so as we go from solid to liquid, and then aqueous, and then gas, looking at all these here, we see an overall increase in entropy or increase in disorder. So solid, low entropy, very ordered. Gas, high entropy, very disordered. So a question you would see that incorporates this idea of spontaneity is which reaction will occur spontaneously. So we're looking for exothermic, giving off energy, and we're looking for high entropy, lots of disorder or randomness. So a reaction must be spontaneous if the results in the products, what you end up with, have a lower potential energy because we are exothermic, giving off energy, so we have less energy at the end, and we are high entropy, so more disorder or more randomness. So choice C, lower potential energy, more randomness. Let's check your understanding. Can you determine if a reaction is spontaneous? At this point, you should be able to determine if a reaction is endothermic or exothermic. Use table I to identify the type of reaction and determine if a reaction is spontaneous.